So, welcome to this particular presentation. Coming to this particular presentation, we can see a reservoir mass curve technique, various zones of the reservoirs and how to estimate the capacity for a given demand. As far as the reservoir is nothing but, let us consider this is the flow. So, as we have estimated what is the peak flow in the hydrograph technique, one of the popular method. So, there are number of methods for estimation of the peak flow, and one which we have seen the hydrograph technique here, how to estimate the peak flow. So, this peak flow is known here. Now, this water according to the requirement, this is the available water, we know now how much is the demand, and accordingly we have to see the reservoir has to be formed by construction of a dam across a river. So, this is the dam, and coming to this particular one, this over this one, the spillway, this is the dam. So, before we go to the structural analysis part of this particular structure and hydrological part, coming to this one, as a result of this obstruction there is a gradual rise in the water level, and this particular level, this we called as the backwater curve, dy by dx S naught minus Sf divided by 1 minus q square t divided by GAQ. So, this is the backwater curve. The profile of this particular curve can be studied from open channel hydraulics, where S naught is the bed slope, Sf is the friction slope, Q is the discharge, T is the top width, G is the acceleration, A is the area. So, this is the another part of the course. As far as this curve, we called as a backwater curve as the relationship between this is the distance, that is the length of the river, and the depth of flow. As the length of river, if from here if you say point here, that is x here. So, the direction, this is the direction of river is x, the depth of flow in the river is y, and coming to this relationship we can see here, as the x increases, y also increases, we say dy by dx is equal to positive. So, this dy by dx positive, we call this curve as a backwater curve. That means this curve is very important in the reservoir design. That means it clearly shows up to what stretch of the river the depth of flow again from here uniform. So, from here the depth is gradually varying. So, we called as a gradually varied flow GVF. So, here we called as uniform flow. So, beyond this one uniform flow, and here variation. So, this depth has to be estimated by integration of this equation, that is open channel hydraulics. Coming to this particular our analysis, this height of the dam, this height of the dam has to be analyzed from the existing area. So, the area by the upstream side, this particular area on the upstream side we called as foreshore area. This entire area we called as a foreshore area. And here we have the two things, what is the height of the dam. That means coming to the first one here, from the stage discharge relationships, this is the value of Q and stage. So, we have from hydrological analysis a stage discharge relationship has to be predicted, what is the relation between the discharge, and this relation can be obtained at a control section, exactly the dam section. So if this is the depth of water, this is the flow in the river. So that is the stage discharge. So now we want to calculate now from this one what is the discharge, or we can say what is the volume. This volume, this is the available flow, and this location where we are constructing this particular reservoir, we have to see the ground level here, how is this valley and what is the maximum value of water that can be stored from our surveying, that is the plotting the contours and developing. So coming to this particular one, this entire on the upstream side of the dam, this entire area on this upstream side we called as a foreshore area. In this foreshore area, you are supposed to calculate the following information. This information is from your surveying. So this is area, this is the area. This entire foreshore area on the upstream side of the dam, approximately locate the center line, locate the center line, and using the block leveling, the contour map has to be developed in this one. So the contour is nothing but line joining the points of equal elevation, points of equal elevation. Means I fix the center line and the longitudinal directions, normally the intervals are taken around 20 to 30 meters in the practice. So you fix it at every 20, 30. So let us say this is point A, B, C, D, E. So the longitudinal points we have fixed, the center line we have fixed, then fix in the transverse direction, usually the left and right. This is the transverse direction. At every cross section, normally, so this is the maximum nearest point. So from this particular one, so normally we will take it at an intervals from the center line. This is the center line at 1.5, 3, 6 and 9 meters to the left. Similarly, same thing 1, 3, 6, 9. So on both sides of the center line at a distance of 1.5, 3, 6, 9, you can establish the various points and you can, using your leveling method, that is height of instrument method or the rise and fall method, either using the theodolite or with reference to dumpy level or the total station today, we can estimate like this the entire area. You take the readings and all these readings at various points, you establish the various points in the foreshore area both to the left and right and calculate the reducible levels of all these points. Once you calculate all these reducible levels, we can join the points of equal elevation, that is nothing but the contours. So you can develop the contour map or contour plan from this one. Let us develop, this is one contour, this is the another contour, this is the another contour, so this is the another contour and this is the, so like this I have developed a contour plan, and it's a rising elevation from lower to higher, and knowing the contour interval and using the planimeter keep the planimeter on the contour and rotate it and calculate the area of every area enclosed by each contour. So, now knowing the area contour interval, so we can calculate what is the volumes, what is the volume. So, these volumes A1, A2, A3 like this, similarly V1, V2, V3, V4. So, these volumes are estimated either by trapezoidal or prismoidal formulas according to surveying principles. Use these particular rules and get the values of volumes. Now, you know the contour interval, that is the elevation, and you know the volume, now you know the area. So, this is the elevation, and now you plot the various elevations at different contours, 100, 110, 120, 130, 140, and you can calculate with reference to this one a plot. Finally, a graph is to be drawn. This graph is like this. So, this is the elevation, this is the volume, this is the area. So, we have the interval, that is an elevation versus the volume. So, as the elevation increases, volume increases, that means the depth of or height of the dam increases, volume of the area or the volume of water, that is also increasing. So, coming to this one, this is one curve, and coming to the elevation versus the area, this is the curve. So, this is the curve volume versus the elevation, and this is the curve elevation versus area. So, now knowing this particular one, we can calculate with the help of this particular contour map here. As far as the stage discharge relationship, the stage discharge relationship here, this is the stage and discharge. We know with reference to the given volume, that means how much volume of water it is required, and accordingly what is the depth of the flow, the height. We can know from this one, we see how much volume of water that is required for our purpose where we are constructing the dam. The dam site, how much water to be stored. The amount of water that you are going to store is based on the demand, how much you required. So, you know the demand calculation by the irrigation requirements. Now, we know the volume of water required for the irrigation purpose. So, this volume, plot a line and which tells this is the point and this is the area. So, these 2 points here, now with the results, once you can plot it here, once we can get it here by storing our volume of water for irrigation, this much volume of water to be stored for irrigation. if this much volume of water is stored at the dam site, how much area is going to submerge on the upstream side, and also what is the height of the dam to be constructed. So, this is how, using this one, this is the height of the dam, this is the area of submergence. This is the area of submergence, this is the volume of water that is going to be area of the height of the dam to be required, and according to this particular elevation, adding some additional factor, we are going to decide the height of this dam. So, up to what height you have to store, or based on this elevation and volume, how much height the dam to be constructed based on the area of the submergence. So, this is a very important one. It is area elevation capacity curve, elevation, area, volume, capacity or area. Elevation, volume, area, the capacity curve is to be first drawn, and using our demand and the stage discharge curve, and we can plot the height of the dam. So, now coming to this particular one, this information, this curve is required to represent the ground situation, that is indirectly this location, how much water can be stored and how much water is required, and accordingly the height of the dam is decided. Coming to this height of the dam here, coming to this height of the dam here, this is how the height of the dam now decided. Now, let us see what are the various zones, zones of storage. As far as the zones of storage, this is the dam over which the spillway. So, we decide 3 levels. So, now here we have the minimum level, normal level and FRL. FRL means full reservoir level. So, now these levels are very important, and a minimum level means as the flow during the floods, the floods carries lot of sediment particles. Once the particles enters into the dam, the kinetic energy is converted to pressure energy, and the energy velocity decreases, particles cannot move and particles comes down. That means the space which we reserved for the particles, sediment particles, is known as the dead storage. This space is known as the dead storage. The dead storage means all sediment particles should not go out of the dam and particles should settle down, and whenever you are taking the sluice level, this is the sluice, an outlet, the water should go. The sluice level is always above the minimum storage or dead storage level. above the minimum level, and that means this particle should not go through the pipe and should not cause any blockage. That is the main purpose of this first one, all the sediments to be settled well within this particular space, and means that space is completely reserved for the sediment particles. And the amount of water which it is required, if it is required for irrigation purpose, thus that water is used for irrigation means the quantity of water which is required for irrigation is stored between the depths, normal depth, minimum level, which is known as the useful storage. This is the useful storage. Above the normal level, whenever the flow above the mean flow, and when it reaches to the floods, the peak flow, that highest level is known as full reservoir level. Means beyond this level no water is allowed to store, and anything beyond FRL the water has to be released. This is a surplus water or excess water, this should be released through the spillway. The surplus water should be released through the spillway. So these are the various zones which we have. So dead storage, useful storage, and this zone is known as the flood storage. During the floods, excess water we just store, and beyond FRL we are going to release the water and lift the gates and then release the water. Coming to these particular zones, the various definitions related to this dead storage, minimum drawdown level. Let me explain these particular storage spaces. We have these storage spaces, and coming to the first one, FRL, full reservoir level. This is the level corresponds to both storages that is active and inactive. So FRL is nothing but the maximum storage capacity. This includes both levels. One is corresponding to active storage, that means useful storage. Below the active, inactive, that is nothing but the dead storage. That means up to that particular level, whatever the water can be used for irrigation, hydropower, various purpose, water supply, etc. So that is the meaning of what is FRL. Coming to the second one, minimum drawdown level. It is a level below which a reservoir will not be drawdown to maintain minimum head required for projects. This is the hydropower. Coming to the next one, you can see here, minimum drawdown level, MDDL. So that means in a dam some level you maintain the water below which it is not allowed to draw down. Draw down means the falling of the water level, because our power, especially for hydropower, power is equal to rho g q into h. The discharge, that is the flow, and h is nothing but the head. So if this head, if you not maintain, if you sufficient head you are not able to maintain, or what is the minimum head required for the turbine, if you are not maintaining, the turbine will not run. That means power will not be produced or income is lost. That is why in any case we fix some particular levels below which the water level should not fall. That level is known as the minimum drawdown level. Coming to the dead storage level, it is the level below which no outlets are provided. To drain means one particular level, this is the level, above that only the pipe is provided. So this is the minimum level. So below this level, water, it should be always it should see that water level should not go beyond this particular level. Water level should be always above. That means if the water level goes below, the outflow or the draining of the water is not possible and silts will enter. So that is called a dead storage or minimum water level, which is normally in summer the water level reaches to this particular level, mostly in summer season, because of no water in the streams. Coming to the next one, level, maximum water level. MWL. This is the water level during the flood, that is ever likely to be attained. Means this is the highest level, HFL, highest flood. That means the water level during the design period of the structure will never cross beyond this one. Even the highest one is the flood. That flood is the highest. During the flood season also, the water level should not go beyond this particular level. That means the up to particular level, once the water reach, we lift the gates and release. So it is a maximum water level, or it is nothing but the highest flood level HFL, during which the water during this particular stage will never cross beyond this level even during the flood, if flood occurs likely to be attained. That is called the maximum water level. Coming to the live storage or useful storage, so it is the water stored between minimum level and the normal level. So useful storage is nothing but the water stored between the minimum level and normal level. How much amount of water stored, that storage is known as the live storage or the useful storage. outlet surcharge and or we will also called as flood storage. Means as we have seen, this is the dam spillway, anything, this is the maximum water level and FRL, full reservoir level. This is the highest level, this is the full reservoir level. Beyond full reservoir level, we do not allow any water to be stored. Means immediately whatever the water between these levels, when it reach, this water is released through the spillway. So that level is known as outlet discharge or flood storage level. The last one is dead storage. Coming to the dead storage, this is the space below the minimum water level. Whatever the below the minimum, below this particular minimum water level, the space which is provided for the accumulation of sediment such that the sediment should not enter through the outlet. That particular storage is known as the dead storage. So these are the various zones of the reservoirs, and so we will see the next one, the capacity calculations. Estimation of reservoir capacity. So our next thing is once we have analyzed these particular levels, the various levels which we considered, and these levels what we fixed it. Now the reservoir capacity, that means the capacity is three things here: the space for the dead storage sediments, space for the useful and flood. So different purpose. So here we are going to estimate based on our demand. How much is our demand? This demand we are considering here, this is a course on irrigation. We consider only irrigation demand, that means how much water is required for the plants. So the two variation, one, there is a flood situation where you can store the water and raise the water level. So when you are having the flood situation, the excess water to be stored in the reservoir, then the demand. When you do not have the water, that is in the summer, when the demand is more than the inflow into the reservoir, you have to release the water. So when the inflow is more than the demand, you store the water, excess water. When the inflow is less than the demand, release whatever the water you have stored. So this is what we are going to see, the analysis of reservoir capacity. Here we require to know the first the ordinates of the mass curve of inflow, that is, one is the water that is going to enter. What is the inflow? That is a hydrological data, that is a hydrograph analysis. From that we are going to estimate the various ordinates of the capacity mass curve of inflow. And the second data which is required on the downstream side, the demand. So the demand here for irrigation, and knowing these two, inflow value and the demand, that is the requirement, we considered here as a constant demand for the purpose, and using this information plotting the mass curve of inflow and the demand curve or line or curve, we are going to estimate the capacity of reservoir. So that is the topic on estimation of reservoir capacity.